Hi guys, welcome back to Depth of ML. I am Saloni and today we'll be solving this question from linear algebra which is around vector spaces and subspaces. So let's see what the question is asking. So the question says which of the following is false. So it's a MCQ question. One of the statements that they have given, one of them is false. So let's see the statements one by one. So they're saying whether every vector space is a subspace of itself. So say V is a vector space. Is it a subspace of itself? I will use this subset or equal to as a subspace of this vector space symbol. So the first part is asking whether a vector space is a subspace of itself. Second part is asking that the subspace of every vector space is itself a vector space. So if I have W which is a subspace of V, then is it a valid vector space? The other question is asking, the third statement is asking whether the intersection of two subspaces of vector space V is a subspace. So suppose V1, I have W1 and W2 which are subspaces of V, then is W1 intersection W2 a subspace of V? Okay. And the fourth statement is asking whether the union of two subspaces of vector space V is a subspace of V. So if I have W1 and W2 which are subspaces of V, is W1 union W2 a subspace of V? Okay. So to solve this question, you should understand what is a vector space, what is a subspace, and if you can understand this is a very easy question to solve. So let's solve this. So before we solve this, I just want to go over the definitions of vector space. So I am able to relate to this while I am explaining it to you what the solution is. So what is a vector space? So vector space is nothing but a set of vectors which has some special properties, and these are the 10 properties. So x, y, z are the vectors which are coming from the vector space V, and C1 and C2 are basically the scalars. So these are scalars and these are vectors. Okay. And there are three sets of properties that a vector space has. So the first property set is additivity or additive properties. The other set is multiplicative properties. And the third set is of closure properties. Okay. So a vector space has additive properties. What it says that it's commutative, it is associative, it has a zero identity, or it's an additive identity, that if I add an element which is the additive identity for that vector space to any vector from that vector space, I should get the same vector back. Okay. And there is a negative element such that if I add a vector and the negative of that particular vector, then I should get the additive identity. Fine. So these are the additive properties. Similarly, we have multiplicative properties where we have a multiplicative identity such that if I multiply the multiplicative identity to any vector from that vector space, I should get the same vector back. Then there is again associativity corresponding to the multiplication of the scalars. So if I am multiplying two scalars, it doesn't matter in what order I am multiplying them to the vector, I should get the same result. Fine. Then this is distributive properties. Actually, these both are distributive properties. So if we are multiplying a scalar with the addition of two vectors, it should be equal to individually multiplying that particular scalar to the vectors and adding them. Similarly, if I'm adding a sum, if I'm multiplying the sum of two scalars to a vector, it should be same as I multiply each of the scalar to the vector and I add them. Okay. So these are multiplicative properties. The third one is closure property, and this is very important because these two properties, additive and multiplicative properties, are basically inherited by the subspaces. When we talk about subspaces, I think it will become more clear. But the subspace, which is basically the subset of a vector space, will always inherit additivity and multiplicativity. The only thing that helps us determine whether it's a valid subspace or not is a closure property. Okay. So we should pay attention to the closure property, and usually this is what helps us determining whether a subspace is, or a set or subset of a vector space is a subspace or not. Okay. So what is this closure property saying is that if I have two vectors x and y which belong to the original vector space V, then any linear combination of those two vectors should also belong to V, right? So if I have x and y which belong to V, then any linear combination of these two vectors should also be in the vector space. Fine. And if I have a vector x in my vector space, then any multiple of that particular vector should be in the vector space itself. Okay, so this is a very important set of properties, and usually it will help you in determining whether subspace is a valid subspace or not. Fine. So this is what I wanted to talk about the vector space. Now let's talk about subspace. So what is a subspace? So subspace S of a vector space V is a subset of V. Okay, so it's, first of all, you should pay attention to this subset word. So when we talked about vector space, we said that it is a set of vectors. Okay, so a lot of students don't look at vector spaces as sets, but we should be looking at them from the point of view of sets. That a subspace S is nothing but a subset of the vector space, because vector space is itself a set of vectors. So it's a subset, and it actually follows these two properties. Okay, if you can just justify these two properties for a subspace, then it's definitely a subspace, because I already told you that additive properties and multiplicative properties are actually inherited from the original vector space always, right? In most of the cases, they will be inherited unless specified. So only thing that you have to the only thing that you have to worry about is actually the closure under the vector addition and closure under the scalar multiplication. Okay, so suppose I have a vector x and a vector y, which belongs to the subspace or the subset that we have defined S. Then any linear combination, it's actually the linear combination. So these two statements combined will say that the linear combination of these two vectors should also be in the set. Okay, and S is closed under the scalar multiplication. So similar thing, that if I have a vector x, then every multiple of that particular vector should be in the subset. And if these two properties are satisfied, right, for every vector that is there in S or the subset that you have defined, that subset will become the subspace. Okay, so I'll just reiterate here that a subset of a vector space V is a subspace if it follows closure properties. Okay, so let's say that I have a vector space which is like all the multiples of x, all the multiples of y, and all the multiples of x and y. Okay, so this is a valid vector space or a subspace. Now if I'm defining S to be this, that I have x, I have 2x, and I have y. Okay, and this is it. So this is a subset, but this is not a subspace, right? Because I have not defined any linear combination like x plus y in this, right? So this will not be a subspace, but it will be a subset. Fine. So now let's go back to our question and try to solve that. Now if you have understood this far, I think this will become very simple for you to understand. Let's look at the first statement. So what is this first statement saying? So it's saying that every vector space is a subspace of itself. Okay, so we know that additive properties and multiplicative properties are already there for the vector space because it was a valid vector space by itself. Then the subspace only needs the closure properties to be satisfied, and vector space already by the properties has the closure properties, right? So the closure properties are always satisfied in a valid vector space. So that's why we can say that this statement is correct, right? So this is correct, that every vector space is a subspace of itself. So the analogy is very similar to something that we have already know in the sets. So every set is actually a subset of itself. It's just that here in vector spaces we have some additional properties, and because a vector space already follows all the properties additive, multiplicative, and closure, so it's a valid subspace. Because it's a subset of itself and also it follows the closure properties, right? So every vector space is a subspace of itself. So this is correct, right? Now let's look at the second statement. Every subspace of a vector space is itself a vector space. Okay, so it's saying that every subspace, right? So W is a subspace of V. Then is it asking whether W is a vector space or not? Okay, so So what do we know about the vector space, right? So we know that a vector space should have additive properties, multiplicative properties, and also the closure properties, right? So a subspace, as I already told you, that it already inherits the additive properties, the multiplicative properties, and we ensure that the closure properties also satisfy. So these three properties, the set of these three properties was already satisfied in a subspace, right? So hence a subspace is actually a vector space itself. Fine. So a subspace is actually a vector space itself because it satisfies all the properties of the vector space, right? So additive is there because this is inherited from the vector space. Then multiplicative is also there. Multiplicative is also there, and also closure properties are satisfied in subspace, right? So closure is also there. So these three sets of properties is already satisfied. Hence this is correct. Fine. Now let's look at the third statement. The intersection of any two subspaces of a vector space is a subspace. Okay. So the intersection of two subspaces of a vector space is a subspace. Right. So let's look at this. So if I can prove the closure properties for this set W1 intersection W2, I will be able to show that this is a valid subspace. Okay. So what are the closure properties? That if X belongs to this set W1 intersection W2, then Cx should also belong to W1 intersection W2. Okay. So say X belongs to W1 and X also belongs to W2. Okay. So X belongs to W1, then we know that Cx will also belong to W1 because this is a valid subspace. Similarly, Cx will also belong to W2 because this is a valid subspace. W2 is a valid subspace. So if Cx belong to both the subspaces, then Cx will also belong to W1 intersection W2, right? Because it belongs to both the sets, it will also belong to the intersection of the set. Hence, Cx will belong to W1 intersection W2. Right. So if X belongs to this particular set, I have proved that any multiple of that particular vector also belongs to this particular set. Hence, my first property is satisfied. Okay. Let me look at the other property, which is the second property itself. So I have two vectors which belong to X and Y. Okay. So there are two vectors that I have two vectors X and Y which belong to W1 and W2 and basically the intersection. So if I can prove to prove that C1x plus C2y for C1 and C2 in R for all basically they belong to W1 intersection W2, then I have proved that these two vectors linear combination is there in this and hence it will be a subspace. Okay. So I'll do a similar argument here as well. So I know that X belongs to W1 and Y also belongs to W1, right? Similarly, I know that X and Y belong to W2 also, right? Because this was a valid subspace, it means that C1x plus C2x, C2y also belong, C2y also belongs to W2, right? Similarly, I can write here as well that C1x plus C2y also belongs to W2, right? So now this particular vector, and it can be any combination, right? So I have not defined any C1 and C2. I'm saying for all C1 and C2 that are in R, this is true, right? Because they are valid subspaces. So if this belongs to W2, this is W1 actually. So if this belongs to W1 and this belongs to W2, then it will belong to the intersection also, right? So C1x plus C2y also belongs to the intersection. W1 intersection W2, right? So I wanted to prove this for all C1 and C2 belonging to R or the scalar group or the R0 vector space. So I wanted to prove this and I have proved. So my second property is also proved, right? So the closure is there. So, and I know that rest of the properties are automatically here for these two vector spaces or subspaces. So this is actually correct, right? Because I just proved to you that closure W1 and intersection W2 is closed, right? Or follows the closure property. Follows closure property. Hence it's a subspace. Hence it's a valid subspace. Okay, so now only one option is left, and because this is an MCQ, so this must be the answer. But let's look at this and understand why this is false. Okay, so union of any two subspaces of a vector space is a subspace. This is not the correct statement. Okay, so what the question or the statement is saying, that if W1 and W2 are two subspaces of the vector space V, then W1 union W2 is also subspace of V, right? To prove. Okay, so when you have to prove these kind of things, right, even if you can present one example which negates this particular statement, you are done. Okay, for proving something is true, you have to be very generic and do a proof like I did just before for W1 intersection W2. But to disapprove, if you can just present one example, that's enough, right? This is the proof itself that, okay, for this particular instance it's not working, hence the statement is not true. So I'll do the similar thing here. So I will give you a very simple, very basic example to understand this. Okay, so let's assume that the vector space V is actually R2. Okay, and W1 is equals to X axis, and W1 is equals to X axis, and W2 is equals to Y axis. Okay, so first of all, see that W1 and W2 are valid subspaces, because any vector that you have here, right? So any vector you have here, here, so any multiple of this will always lie on X axis. It can go back side also, like then the negative side, or if you add two vectors from this particular axis, they'll still lie on this particular axis, right? So this is a valid subspace. Similarly, W2 being the y axis is actually the valid subspace, right? Any vector you take here, any vector that you take here will be a valid vector that lies in this subspace only. So the closure properties are already satisfied, right? And 0 is already there. 0 is also something that creates an issue when we are trying to prove whether a subspace is valid or not. So you should also check for 0, whether 0 belongs to the subspace. But because they were already valid subspaces, so their union and intersection will automatically contain the 0, right? So now let's see. Okay, now let me take two vectors. Okay, so I have a vector 1 which is V1 vector. So let me take it to be 1, 0. Okay, so this is my vector. Let me write it like this. So this is my vector 1, 0. Okay, and let me take the another vector V2. Okay, so 0, 1. Fine. So this is my other vector 0, 1. Okay, now V1 belongs to the first subspace, which is W1. V2 belongs to the other subspace, W2, and obviously their multiples belong to W1 and W2 respectively, right? Now if I add W1 plus W2, right, what will I get? I'll get a vector 1, 1, right? Now if I take union of these two subspaces, what will I get? All the vectors that are on x-axis and all the vectors are on y-axis, right? But when I add these two vectors, the vector I'm getting is here. So the vector I'm getting is this. This is 1, 1, right? So is 1, 1 part of the union? Does this belong to W1 union W2? So all the vectors here and all the vectors here only, right? So these vectors are not part of this, right? So this is not part of this W1 union W2, and hence the union of any two subspaces might or might not be a subspace. Okay, so I've given you this one proof, that one instance where it's not true. So it's not true for any, like, it's not true in general, right? There might be some cases where W1 union W2 is actually the subspace, a valid subspace, but if you are asking us generically that W1 union W2 is always a subspace, it's not true, right? And I have shown you one example of that, right? So this is false. So the correct answer for this particular question was this. So the union of two subspaces of a vector space is not always a valid subspace. Fine. So let's see how the students replied to this particular question. So I had asked this question on the Telegram group that we have, the public Telegram group where we actually discuss a lot of things about the GATE DA. So if you're not already part for it and you're preparing for GATE DA, you might want to check out the Telegram group. So I had asked the same question on the Telegram today, and a lot of students replied, and these were the stats of that. So you can see that many of these students thought that every subspace of a vector space is not a vector space. So there were students who actually incorrectly answered this question. So I'm hoping that after this video, you will be able to answer this correctly, and some of your concepts regarding subspaces and vector spaces have been cleared. Thank you. Thanks for watching. And if you want to join our Telegram group, I'll attach the link in the description below. You can also check out our courses on the GATE DA preparation on our website, for which you will find the link in the description. Thank you.